Greetings, this is Rick Powers from Western Technical College, Introductory Statistics. And this lesson today is about linear relationships and correlation. And this lesson specifically is about understanding the input and output of SALT using linear relationships. Consider the dataset placebo exercise. I go out to SALT and I'm going to upload placebo exercise. There are many variables that we could choose, but for this lesson, we will look at numbers that change with the age of the person. Let's begin with age versus systolic blood pressure. The goal is to find out what happens to systolic blood pressure when age changes. In general, when working with two variables, we consider changes in one variable to cause the changes in the other. This isn't always the case, but surely we can know systolic blood pressure does not change your age, but the other way around. Age might change your systolic blood pressure. So then after uploading the data, we choose the variables age and SYST. Click then on regression. Then choose age for the explanatory variable on the x-axis and SYST for the response variable on the y-axis. Recall the x-axis is horizontal and the y-axis is vertical. So we select age for x and SYST for y. Note that the axes are labeled with the data values. For example, a 35-year-old had a systolic blood pressure of about 128. So the visual information for this data appears to be a cloud, a scattered collection of dots. That's the most likely result when looking at a dot plot of data. Then our goal is to see if the cloud has a tendency to follow an upward or a downward trend. That is, what happens to systolic blood pressure as age increases? The yellow line indicates that there is a positive relationship. Positive relationship means that systolic blood pressure increases as age increases. Now, we want to consider if this is just a random event, or can we prove that this is not just by chance? We will use the correlation in order to understand this. Be sure to watch this video about correlation. When using SALT, it gives us the correlation coefficient. In this case, 3.706. It is listed below the graph. If you look below the graph, correlation 0.3706. As described in the video, this is not a really strong relationship. This data is cloudy or fuzzy. It is not all close to the straight line. You can see it here. They're a collection of dots. They're not on the line. They're not, some of them are not even close to it. And so it's kind of a cloud, kind of fuzzy. The correlation coefficient is telling us, since it's not close to the number 1, that this is not a strong relationship. However, is the relationship just a random chance, or can we say that there is a change in systolic blood pressure due to age? More specifically, what we are dealing with is a change in the average. Does the average systolic blood pressure change for older versus younger? By looking at the line and the data, we do see a trend. The line starts at about 115 for age 18 and then goes to 140 for age 65. This line is an estimate of the average for systolic blood pressure for different values of the age. In order to do hypothesis testing, be sure to view this video. The SALT software will give us the important numbers for us to do the hypothesis test. We've already seen the correlation coefficient. That has the symbol R, small r, or sometimes capital R. Degrees of freedom, in this case, is n minus 2, where n is the number of dots or observations. SALT gives us that number as well. We see degrees of freedom here, 63. There is a formula for the relationship of R to the t value for the data. On some homework problems, you'll use this formula. Here's the formula. T is equal to R multiplied by the square root of top of the fraction n minus 2, bottom of the fraction 1 minus R squared. Fortunately, in this case, SALT does that calculation for us. The t-score is located in the coefficient summary table in the second line where it says age. We go over and we see the t-score. If we had used the formula using R, we could put that into the t-score and also find that number this way. Then based on the t-score and the degrees of freedom, using a t-tailed test, we get the p-value. The p-value is listed as 2.376 e negative 3. Note that this is in scientific notation. A negative exponent indicates a small number. So in decimal form, this is 0.002376. The decimal point moves 3 places to the left when it's e negative 3. This appears in 2 places in SALT. In the model summary table, clear over here, and in the coefficient summary table, it's the same number down there, across from the word age. The p-value is certainly less than alpha, so we reject the null hypothesis. So we have proven that this positive linear relationship is not just a random chance. In other words, the average systolic blood pressure increases as age increases. Now, let's consider age versus weight. Go back to the data set. And now we will choose weight, just WT as a variable. And then under regression, we choose weight as the response variable. Once again, the data is in a cloud. But now the yellow line is almost horizontal, indicating the average weight does not change much with age. The p-value is 3.414 e negative 1 in decimal form, 0.3414. Our decision now is to say there is not enough evidence to prove that the average weight of people will change with age.